Good afternoon, Radu. Hello,
Hi.
Radu. Can you
Yes.
hear me?
Yes, I can
Yes,
hear
yes,
you.
yeah, good. Yes, yeah. So Shen, you can take the time to check your slides. Yeah, if you like. Yeah.
Yes, that would be a nice idea. I can share. Actually, this should be maybe the best. Does it work? Do you see my presentation now?
Oh, sure. Yeah. No problem. Okay. Yeah. Yeah.
Just a brown, sorry, a blue screen with the DTU logo on, basically.
Oh, okay. Yes. Okay. I see. Okay. Okay. Why
And
don't we
then
just start? If we can start now. I think it
then I
only
can,
was 1 minute
yeah,
first. Yeah.
okay.
Yeah. Okay. Yeah.
If you can
Please
see
do.
my presentation, then yeah, we can start.
Mm-hmm.
Okay.
Who will be the second speaker?
Well, according to the program, it's Professor Ryukhtin.
You can get it.
Yeah. Rookie.
Is
Yeah.
he
Rookie.
inside or not inside?
I don't see him in the presentation list, in the participants list.
No, he's here.
So,
Okay. Okay. Mm-hmm.
Okay.
Okay. Why don't we just start? Okay. This is the section 4 of the day 3 meeting, and Professor Wang and me, I'm Tim Lee, and we chair the section. Okay, the first section is from Denmark. Professor Ruda, I'm not sure how to pronounce your name. Sorry about that.
it's fine. Radu is the easiest.
Right. Okay. Okay. The title is Fabrication Possibility for Silicon Nitride, Metasurface to Enhance High-Order Nonlinearities. Yeah. Please go ahead.
So, yeah, thank you very much for the presentation, and thanks for inviting and allowing me to present this work at the conference. Yeah, as mentioned, we come from DTU, and yeah, I'm so the main promoter or the main responsible for this work, I would say, is Maxim, and then I added Osamu because he did some nice measurements on the metasurfaces that we made, me and Andrei, and just a quick overview. That's where we are. And that is what Google Maps tell me that it will take to reach Chernivtsi. Happily in one way, it was nice when we visited, but sadly it's a bit more difficult now. And well, it's good that it can be organized in an online format. So yep, it takes a bit, but it should be possible, hopefully, in the near future. If we zoom in this spot over here, maybe I should put the laser pointer. Here we are. Then this is the DTU campus, and our building is down here. And next to the building, we have a nice garden where we do some of our outdoor activities. That's the group as it is now, with some alumni and guests. And Maxim, as I said, the main promoter, he just finished his PhD on these surfaces. What we are trying to do, or what yes, in this project, is to investigate both theoretical and experimentally the generation of third harmonic from visible to UV using metasurfaces. So the idea is something like this: we have some structures that if we illuminate with a certain frequency, then obviously being the third harmonic, we get the third time the frequency out, and hopefully enhanced. So in terms of problem formulation, we have a surface that has a certain pattern of, in our case, falls in a rectangular lattice. We come with light, and as I said, we get out the third harmonic. And in the linear regime, everything looks nice. So compared to the non-pattern membrane, when we have a pattern membrane, we have some very deep resonances. That means that field is absorbed within the membrane in this at this wavelengths, and then we can hope that because the field is absorbed, we get some enhanced nonlinearities in at specific wavelengths. And if we concentrate on this one, that's mainly because it's easy to access with the lasers that our collaborators have. Then we made some let's say some simulations with to try to find out the dependency on the film thickness, and it's roughly linear, and the same with the period of the grating. So we can use this to the film thickness and the period to, let's say, roughly tune this frequency. And then we have also a linear, but with a negative slope dependency on this hole diameter. But if you look at it, then the resonance wavelength shifts very, very little, 4 nanometers, with almost doubling the hole diameter. So we use this one only for extremely fine tuning of the resonance. But they are generally quite linear. Maybe here there is some kind of quadratic shape, but because the resonance is because it varies so little, we are not really worried about that. So in the nonlinear regime, things are a bit different, because obviously now we come with a pulse, and if we have our pulse centered on the resonance wavelength, then we can see in the case of non-patterned, we have a third harmonic generation, but the intensity is much smaller than the one in the case of pattern. A zoom in here shows us several orders of magnitude difference. The baseline here, it's different, because basically we don't really wait enough time in the simulations for all the energy to get out of the system when we have the pattern metasurfaces, just because it's incredibly long, and then we still have some residual energy in it, and that's why the baseline is so high, sorry, in the case of pattern membrane. However, what we discovered is that if we change the bandwidth of the pulse, so now we have a pulse that it's much shorter, so much broader bandwidth, we start to hardly see any difference in between the pattern and non-pattern membrane. And if we again zoom in here, we see that instead of several orders of magnitude, we are talking about hardly above 1 as an enhancement factor. So if we want to put them one next to each other, this is the pattern membrane and the non-pattern in the case of narrow bandwidth long pulse, and this is the same structure, but in this case we have broad bandwidth and pulse that will so the effect of the structuring basically disappears in this case. We'll talk a bit more about it afterwards, but now in terms of fabrication, because that's in a way what what this talk is mainly about, we have a relatively standard process flow. So we start with a silicon wafer. We deposit silicon nitride. It's actually silicon-rich silicon nitride, and that is because this way we both have a bit higher nonlinear coefficient, but also, more importantly, from the fabrication point of view, the membranes are less stressed at the end, so that we can make bigger membrane or thinner membrane without breaking them. Then we do an e-beam exposure and etch the silicon nitride on the top layer. We do a UV lithography and etch the silicon nitride on the bottom layer. And then when we put everything in KOH, we etch the silicon from beneath, and we have our membrane with the holes. So it seems quite a straight process. I'll show you a few issues that we have both here basically and here. And the first one with etching, what happens is that after etching, we saw this kind of structure. So instead of having nice round shapes, the holes were, in our opinion, quite ugly looking. And not only that, but they weren't at all uniform over the metasurface. You can see that some are bigger, some are smaller, some are not at all. Most of them are not at all, I would say, in this same image. However, if we look at the resist, the resist look nice. So after the E-beam exposure, everything looked okay. We have some very well defined circles. We see some problems or some debris, let's say, in the hole, but nothing that would make us think that the hole should end up so badly. So, and also, if we compare the uniformity, that's the resist, and it's nice. We don't have any problems with whole size over a larger area and so on. The solution ends up being that, or the problem ends up being the etcher that we were using. So as soon as we changed it to a different etching machine, different recipe, bit more advanced, but also more controlled, then all of a sudden we have some very nice silicon nitride holes. I mean, if you compare where we started and where we ended, it's quite a big difference, I would say. And also, in terms of dimensions, we are aiming for 200 nanometers, and we have a plus minus, let's say, 3 nanometers range. We have better statistic than just these two numbers, but we are in that range. So now that the silicon nitride was etching for the nanoscale was solved, we thought everything is fine, but it turns out that we have some the last step that we expected it to be no problem at all. It turned out to be a bit more complex. So this is a view from the back side of the membrane, and that's so the brown is the silicon nitride. This very thin white is the undercut. So this is silicon nitride on silicon. This white is only silicon nitride, basically just a small undercut, because as we etch through 350 microns of silicon wafer, then although the selectivity of the KOH with different crystallographic plane is huge, is not infinite. So we have a small undercut. That's not a problem. What we discovered, though, is that although we have a square opening, the membrane is rectangular, and that made absolutely no sense to us. And we were trying to figure out what's going on. As well, sometimes we have a nice square membrane, and we have a nice square opening, and we have a nice square membrane. So it didn't seem to have almost any relation between the opening and how the shape of the membrane ends up. Also, the membrane itself was bigger than it was supposed to be, and because of that, since we are working at the limit of what even low stress silicon nitride can support, we start to have cracks like this hole here or this one here in the top membrane that we'd rather avoid. So we decided, since we couldn't figure out what is going on, we decided to cleave some membranes and try to see the profile of the silicon etch. So when we did that, we discovered that rather than having so this is silicon, this is basically air, and rather than having a nice 1-1-1 etch direction, we have some kinks here that made it, we were expecting basically this to be the profile, that makes the membrane bigger, and that's one issue. But also the fact that we have something happening here means that we are not controlling, this is the membrane, the part, we are not controlling some chemistry at this level. And indeed, the solution is what I mentioned before, that the KOH rate, H rate on the 111 plane is not zero. So what that means, funnily enough, is that when you have big structures, you don't care. But when the holes are very close to each other, then this small underedge ends up reaching the small underedge from the other hole, and then it creates an extra edge plane in that on the top here. So to basically what happens is, after we do this, then when we start to KOH edge, although we start here, but we also start slowly to edge up here at the membrane, and that actually explain all our problems, because then the pattern, if the pattern is in a rectangular shape, then we have a rectangular structure, the rectangular membrane. It's also bigger than it's supposed to be, because there is the underedge here that makes it bigger. So we end up with a structure something like this, that is very similar to what we saw in our in our experiments. So now that we know that, we also know how to address it. We cannot really do anything about it, but we can make the pattern a tiny bit smaller, such that the whole opening here is still within the proportions that the silicon nitride membrane holds, and as well we can make sure that we always have a rectangular pattern that matches the opening. So so with that, we pretty much solve this thing. So I will conclude with from the simulations, there is this interesting dependency of the terahertz efficiency enhancement with the source bandwidth, and it would be nice to study this. It seems we have some initial simulations. I didn't show them here because they are not fully interpreted yet, but it seems that we have this very dependency, let's say, and kind of the optimal is when the laser bandwidth and the resonance bandwidth matches, and then farther you go in either directions, it gets worse. And in a way, it kind of makes sense from a coupling point of view. Then it's it's the optimal coupling at that point. But as I said, we need to look to make sure that this interpretation is right, and it would be nice to check the experiment, to be checked experimentally. That's a bit more difficult because we will have to be able to modulate the pulse width, and I'm not sure our collaborators will, for nonlinear measurements, will be able to do that. And right now we have a nice, good understanding of the fabrication process that took a while, but we are in the right place now, and we can do these membranes basically without too much of a trouble, and we know what to do, how to do to get our membranes. And with that, I will close with some field images of our resonances, and well, thank you for your attention. And if any questions, I'm here to answer them.
Okay, thank you very much. Now the talk's open for discussions. Oh, Professor Groski.
Thank you for nice presentation, Mikhail Vohorsky from Chernivtsi National University. So my understanding that periods between those dots are actually like define which laser frequency can be transformed, right?
Yes, so it's one of the parameters. If we look, let me go back to it here, right? So the period is one of the parameters that can define the frequency or the wavelength, however you want to call it. There is also the film thickness, and the hole diameter. But I would say the hole diameter is very, yeah, it's not that important in a way.
Okay, so my question then, as I understand, holes in any way have some size, and also important the distance between holes. And since hole as well can't be like real dot, means without size, what are the real limitation on input frequencies based on this geometry?
So you mean how high in frequency can we go, or
Yes, means
what are the
you told
fabrication?
that it is optical frequencies, but is here any limitation or any frequency from optical spectrum
So
can be
basically, if I understand your question right, basically what happens is you are perfectly right that the limitation actually is in the hole diameter, basically, because we can make them smaller and smaller, but only up to a certain point. That up to a certain point in our case is it's somewhere around 75, 80 nanometers. That makes a resonance period somewhere in the 150, 200 nanometers, the minimum that we can properly control. And that will bring the resonance wavelength in the range of somewhere like, I think, 300 nanometers, if I remember rightly. So it's just below UV light, just below visible into UV light that we can do. Going on in the other direction is not really a problem because you can always make them bigger.
Okay, got it. Thank you.
Okay, thank you very much. Just well, let's keep the time. So maybe let's move on to the next talk.
Yes, I will stop sharing my presentation.
Okay. The next talk is from Professor Ryukhtin from Czech Republic. The title is Investigation of Structures and Dynamic of Flux Lines Lattices and Skyrmions using Neutron Scattering. Yeah, Professor Ryukhtin, yeah, please go ahead.
Yeah. Thank you for introduction. I'm not professor, just doctor. I represent Nuclear Physics Institute of Czech Academy of Science. And now I want to demonstrate some using how we can use the neutron scattering in order to study structures of.
So sorry, can you share a different screen because you're sharing the preview?
Sorry, which screen? Yeah, maybe I shared side screen. Yeah.
I think you shared both screens, or maybe just preview. Yeah. I don't know.
I'm sorry. Like this is better.
No, Professor Ryukhtin, right now you are sharing double screens.
Yeah, you share the presenter view, I think, not the presentation view.
Screen.
Okay.
This screen, you mean?
Now it's better, yeah.
Okay,
perfect.
now it's good.
Okay.
Yep.
Sorry for this.
Yeah, nice. Thank you.
So actually, I will talk about magnetic vortices in superconductors, which can be studied using small angular neutron scattering, flux line lattices in some unconventional superconductors, cerium cobalt indium 5, strontium rutinates, and tantalum nickel carbide.
There are some problems with sound.
What kind of problem?
Now it's okay.
Can you hear me?
Yes.
Now it's okay, yeah.
Sorry. So this is outlook of my talk. I will talk about flux line lattices in unconventional superconductors. And second part of the talk will be dynamics, slow dynamics of magnetic fermion lattices in magnesium.
Excuse me, Professor
Yeah.
Ryukhtin.
Again.
There's still some problem of your voice. Yeah.
And now better? No.
Now it's better. Yeah. Now it's better.
Oh, I'm so sorry. So few words about superconductivity. It was most of you might know, but it was discovered by
Always is the first couple word is clear, and then I cannot hear the. I think there's some kind of interference, something like that.
Yeah, it's strange because in the morning it was okay. I use the same system. Now it's better or worse, or what happened?
Now it's
what
really
should
loud and clear.
Now it's better. Yes, very clear.
Yeah, but what happened next? It's become worse. Yes.
Oh no. It's intermittent.
Sorry for this.
Yeah, that's all
So,
right. That's not in our expertise. Okay.
So if we are talking about simple superconductors, there is a well-known Meissner effect that superconductor in superconducting state doesn't like magnetism, so it's expelled. For example, you can use it for limitation of magnets.
I'm sorry, it's not good. We don't hear you.
You don't hear me. Yeah, what should I do?
Try turning off the video. Maybe that's gonna help. Or just speak slower, I guess. That should be fine.
Yeah, video, you mean? Okay.
Yeah, maybe you can just turn off your video. Yeah.
Yeah. So, so when you cool down superconductor, can you hear me?
Yes.
Yeah. Okay. So it comes to so-called Meissner state. Yeah, which you mean due to that superconductor doesn't like the magnetism, let's say. Yeah, they are expelled from a magnetic field. So, for example, you can see in the middle picture the levitation of permanent magnet above IPCO superconductor. But if we are talking about type 2 superconductors, they on their phase diagram is a little bit more complex. Yeah? So, for example, type 1 superconductor have this just Meissner state, yes, which is characterized by critical field. And when you reach magnetic field which is higher than this upper critical field, it turns to normal state. Just magnetism kills superconductivity. And type 2 superconductors, they have this mixed state, which is characterized by vortex lattices, which can go through the superconductor. And the phase diagram looks like this. This yellow area corresponds to mixed state. So it's characterized by lower and upper critical fields. And between these fields, we can study structure of these superconductors using neutron scattering, because they are forming such lines, so-called vortex lattices. Each vortex lattice is a quantum of magnetic quantum formed by rotating current, and because of interaction of these magnetic vortices, they form different structures. And these structures we can study using neutron scattering. So after discovering of superconductivity, roughly 50 years later, it was explained by Bardeen, Copper, and Schiffer using their microscopic theory. The electrons near Fermi surface forms Cooper pairs due to they pairing despite their repulsive Coulomb interaction, because they interact with phonons. And it was well explained for conventional superconductors, which has a very simple pairing S-wave pairing symmetry. But in case of unconventional superconductors, which most of superconductors, high TC or high temperature superconductors are, like cuprates, iron pnictides, heavy fermions, the Cooper pairs interact not with the phonons, but with magnetic excitation. And that is why structure of vortex lattices is more complex. It can be anisotropic, and that is why when you study superconductivity, which is, let's say, because it interacts with the magnetic field which applied to the superconductor. You actually see superconductivity through observing this magnetic field distribution inside the superconductor. So that is why this crystallography of vortex lattices can help to understand what happened inside high temperature superconductors. And since, for example, if we apply some normal field for superconductors, for example, 0.2 Tesla, the distance between vortices, individual vortices, will be in a range of 100 nanometers, which is a perfect range to be observed using small angle neutron scattering. And so the principle is very simple. If you apply a field to superconductor, this is the direction of a field. So all vortices will be oriented in this direction, and then you need to pass neutrons through this superconductor, and you do practically rocking curve measurements. You rotate a little bit with magnet and detect here on 2 theta corresponding spots which correspond, and then you can map structure by scattering from this distribution of magnetic field inside the superconductor. And here are some examples. The simplest, it's a niobium. It's very easy to measure, and this crystal we use for defining the orientation of magnetic field. So it has a threefold symmetry. You see 6 spots, and this is the next order. Magnesium diborate. These all examples which were measured in a reactor at Grenoble as examples how you can use small angle neutron scattering for studying this superconductivity on different compounds. So we started some years ago in Berlin with the measurements of cerium, cobalt, indium-5. It's a quasi-2-dimensional heavy fermion compound, which is known to be like with D-wave symmetry of superconductive state. So for this compound, it's not easy to grow the crystals. But normally all crystals which we grow were oriented using X-ray in lab. And we make mosaics of two orientations of these crystals. Here on this side you see the plate. It's a sample which we measured, and here down is niobium for orientation of magnetic field before we coming to real crystal. So in this experiment we use V4 instrument, small angle instrument in Berlin with sample detector distance 8 meters, and magnetic field was parallel to C axis. So what we observe with symmetry of these spots from vortic lattices was square. Yeah, so you see 4 spots, and at 1 Tesla, 3 and 4 Tesla, and after at 4 Tesla, it comes to a little bit from square to rhombic. You see these angles, beta angles between these spots. At 4 Tesla, it comes to rhombic. But what is interesting with form factor of the structure, it's a constant, practically not dependent on the magnetic field, which is caused by strong Pauli paramagnetism, because in conventional superconductors you observe a fast decay of this form factor. So next we start to do many experiments with strontium rutinate. Yeah, it's interesting compound which is 2D perovskite oxide, but it exhibits superconductivity without copper. So there are some reports that it's S-way superconductor, but some groups still claim that there is no credible evidence of P-way superconductivity. So, but with this superconductor, the upper critical field is very low. So when we apply, we need to apply very low field, and then distance between these flux line lattices is very large. So we practically need to measure in a so-called U-sans regime, so in regime of very small angles. So we tried several instruments in Anstor, in Berlin, and also at Munich reactor, but results were not so good. And finally we come to KWS-3 instrument in Munich, where we finally managed to measure. But this instrument has an elliptical toroidal mirror, yeah, so we can focus our beam much more. Unfortunately, this instrument has some limitations, so we can measure either on 3 meters or 10 meters. So at 3 meters, we observe square symmetry. But when we wanted to measure this dependence of field, dependence of intensity on a field, we could manage to measure just one spot because we come to very, very close to beam stop. And unfortunately, this reactor now is not in operation, so we are waiting. It will operate again. And this is a vortex lattices which we measured at PSI, Willigen. It's a non-central symmetrical superconductor lanthan nickel carbide. So it has a different structure of flux line lattices, depends how you orient the crystal. So for example, here it's parallel to A, B, and C axis. And
here you see 6 spots on threefold symmetry, and down it's a quadratic. And we measured just two fields, 0.6 and 0.006 and 0.1 Tesla. Then it's we try to fit the data with the different models, if it has a full gap or nodal gap, electronic structure of superconductivity, but both of them, some of them is better, some not. It's data is quite noisy, so now it's still in process. So now I come to second part of my talk. It's dynamics of skyrmion lattices is in magnesium silicon. So skyrmion lattices, it's something different than flux line lattices in superconductors. They appear for example, in this case, in chiral magnet, and they are topologically stable. So, for example, on this phase diagram, when you cool down below 29 roughly Kelvin, so on upper field there is a conical orientation of magnetic spins and helical, and but when you reach this area, so-called A phase, so they make such texture which is stabilized by so-called Zoloshinsky-Moria interaction. So they are potential interesting to be used as a data storage or other spintronic devices elements. And for example, static or elastic scattering is quite straightforward. Yeah, it was done some years ago. The scattering looks like similar, like in case of flux line lattices. But we try to use inelastic scattering. And for example, here you can see how the geometry of experiment, which gives you structure, formed by these 3 Q vectors. It's distance around 18 nanometers between them. And we have the second time of chiral skyrmion, so-called block type skyrmion, or they call it baby skyrmion. So when they interact, usually it's a structure, threefold structure here. They are oriented like threefold structure. So we applied, we use neutron spin echo technique, which is based on a principle that a neutron can be rotated and it flies the monochromatic beam. It means all neutrons has roughly the same velocity. But in magnetic field, it starts to rotate. Yeah, and if you, with pi2 flipper, orient all spins of neutron before this precision in magnetic field, and then it go to sample. And here, pi flipper change a phase of this rotation 100 so to pi 180 degrees, and they start to rotate to another direction. And in case there is no change of velocity, so it means neutron doesn't interact with the sample, do not lose energy or do not gain. So at the end, you should come with the same orientation of these neutrons, which can be analyzed with detector analyzer. So in this experiment, we use pyrolytic graphite to find this orientation where we have a 0 position, and then we put a sample in a magnetic field and apply magnetic field up and down. And the data was collected near a breakpoint of scattering from skyrmion. So here it's a results. What we calculated, for example, here is the phase shift of the spin echo profiles in the skyrmion phase as a function of echo time when field was applied up, and same picture when you apply down. And here you can see this energy from these phases. Yeah, we can make a dependence of energy transfer, depends on a QZ vector. And finally, here you can see the dispersion curve. Dispersion curve, which for example, in our case, we estimated this asymmetric dispersion. It should looks like that, but these lines, the dashed lines, it's our experimental limit. Yeah, so here this area is like expansion of our estimated model. With this, I would like to thank to all my collaborators who prepare these samples or collaborate or give idea to these measurements, or instrument responsible for different measurements which we done. And thank you for your attention.
Okay, thank you very much. Okay, because of time, we could have one very short questions. Anyone have questions? Mm-hmm. Okay. Okay, if not, then maybe we will move on to the next talk, because it's we run a bit time over. Mm-hmm. So let's keep the schedule. Okay, thank you very much, Professor.
Thank you.
And okay, I will pass the chair to Professor Wang. And yeah.
Okay, thank you. So the next talk will be given by Professor Podolskiy from the United States. It's the invited talk. The title of his talk is Primordial Metamaterials. Please.
Okay. You see the slides? Can you hear
Yes.
me?
Yes, we can hear you. Yeah.
Yeah,
Good.
Excellent.
Yeah.
Give me a sec. I'm gonna turn on the laser pointer. So I'd like to thank the organizers for actually running the conference. It's a very interesting conference to attend, and I'd like to thank them for inviting me as well. This work is a collaborative work between my group at UMass Lowell, group of Evgeny Narimanov at Purdue, and Dan Wasserman at Texas. And we are still thankful for National Science Foundation for supporting this research. So this is the introduction to the talk. We are talking about metamaterials or about optical composites. And this field has exploded in the last 2 decades or so because mainly of the efforts of nanofabrication industry and nanofabrication research. The sort of hand-wavy arguments for metamaterials or for composite science goes something like this, that we all know that electromagnetic response of media is related to material permittivity, which in turn is related to atom-atom interaction, dipolar interaction primarily, with electromagnetic fields. So we can engineer composites on the scale with the dimensions that are smaller than a wavelength, and then somehow we'll come up with new materials that will have new unusual refractive index properties and enable something like you can see here, that that shows negative refraction of light, or maybe some other interesting phenomena. So this picture that you see here, this is the picture that is often talked about, and I myself has been sort of promoting this picture for a number of years, that when your scale of inhomogeneity inside your material is of the order of your operating wavelength, you're in this photonic crystal regime where the properties of materials are essentially given by the interference of light scattered by multiple inclusions. And then as you make your materials components smaller, smaller, and smaller, you converge to this effective medium regime, where your material does behave like essentially a brick with some effective new parameters. The smaller the scale, the better the effective medium. That's what we've been told. And the nanofabrication industry has been, attempting for a while to fabricate and come up with designs of materials that have smaller and smaller and smaller scales. And they sort of succeeded, but the point of this talk is to actually review a little bit of this research and primarily to show you that this very simple and very intuitive picture is actually fundamentally wrong. And hopefully show you some new regimes that are being available now with the new advances in nanofabrication. So before I start talking about the new advances in nanofabrication, I wanted to review very briefly the electromagnetics that we all learned, sometimes in high school, more so in college. These are Maxwell equations that describe light-matter interaction. We're limited to optical frequencies, so we ignore magnetic response of materials because usually the magnetic response of materials at visible frequencies and optical frequencies is small. But you can repeat whatever I say for mu as well as epsilon. So in time domain, materials respond to light. The response of materials comes through what is called displacement field or polarization field. As I just said, the response is usually dipolar. So that means that your material remains electrically neutral, but your charges rearrange in response to electric field. And this rearrangement of charges takes time. And as a result, the material response is time lagged with respect to electric field. We don't really like to have integral differential equations and solve them. It becomes a very complicated process. So the technique that mathematicians told us to do is to do a Fourier transform of this complicated equation. And that Fourier transform folds the non-trivial time dynamics into frequency dependence of permittivity. And so the frequency dependence of permittivity that we all use, all know and all measure, that's essentially a direct consequence of this time lag of material response. Now, once your permittivity becomes function of frequency, we can mathematically limit ourselves to monochromatic light. We reduce our favorite Maxwell equations to essentially algebraic equations that represent relationship between wave number, which is this k, operating frequency, and permittivity, and electric and magnetic field amplitudes. And we notice that if we assume that the fields inside materials are like plane waves, then those waves have to be transverse, because as you can see, electric field is perpendicular to wave number and magnetic field, and likewise magnetic field is perpendicular to wave number. And then we know that wave vectors and frequencies are related through permittivity through what is called dispersion relation. So that is all nice and well until you get to the actual dynamics of materials and actual nanoscale response of materials. And then you realize that the materials lag the excitation electric field, not just in time, but also in space. So those same electrons that lag in their response to electric field, they also move and they move around inside the material. And as a result, your dipolar response can be at the point that is slightly shifted from the point of your electric field. So this was realized by Pekar back in, as you can see, 1950s. But what this yields is that, again, we don't like integrate differential equations. We're going to do a Fourier transform. And now the spatial dispersion, or the non-locality of response, which you're going to be using interchangeably through this talk, can be folded into wave number dependence of your permittivity. And so, again, so far so good. There is nothing new until you realize that if your permittivity at some wave number and at some frequency goes through zero, then the Maxwell equations that we, again, all know, allow for longitudinal wave propagation. You can see it right here. If your epsilon is zero, then you choose your electric field along your wave number. H is zero, and again, E cross K becomes zero just because they are in the same direction. And so these are new types of waves that supposedly should exist in our materials at essentially frequencies and wave numbers that are selected by this rule. But there is more, because if you remember how the dispersion relation for, say, anisotropic crystals is derived, you basically combine the two responses and you end up with a determinant that looks kind of like this. The important part of this determinant is to see that it is proportional if epsilon does not depend on k to k squared. Once you calculate it, you get a biquadratic equation, and those are your two electromagnetic waves with opposite polarizations and potentially different dispersions. The key point to remember is that if now there is a k dependence in epsilon, you get an equation that is not biquadratic, but of a higher order. And the higher order of the equation means that you have more waves. And so those are the additional waves that I'm going to be talking about throughout this talk. And I'll get to several realizations of these waves, first in metamaterials and then in actual materials. And the waves in actual materials we're going to be calling primordial waves. So first, let's look at the composites, and let's look at that picture that I showed you, that we can introduce effective medium response. And this is an example of a metamaterial. You're looking at an array of metallic, in this case, golden nanowires grown in the dielectric host. So our experimental collaborators, in this case, it's Zayets's group at UK, they can etch away the host materials and essentially have these nanostructured metals aligned, freestanding on substrates. You can see that this is a very anisotropic media. The optical axis is aligned with the metallic nanowires, and we can develop effective medium response for these materials. This is what it looks like. You can see that the two components of permittivity are very different and actually sometimes have different signs. What this means is that the light propagating for the larger wavelength, larger operating wavelength, has hyperbolic dispersion and has very unusual properties. I'll talk about them in a second. That's not the main part of this particular talk, but if you want, I can ask questions about that. What's important is that if you do a characterization of this material, angle-dependent, say, transmission, then you can, so these are the experimental data. This is extinction spectrum, so essentially minus log of transmission as a function of wavelength and angle. And we can calculate the same or model the same behavior with effective medium response. That these are the effective medium calculations. And you can see that they represent each other very well. So basically, this very complicated composite does behave like an effective medium material with very, very strong anisotropy. So this correspondence between effective medium parameters and the material response goes further. People have analyzed the refraction in these materials and actually demonstrated negative refraction of light in these materials experimentally. People looked at the emission the kinetics of molecules inside these materials and shown that whenever this changes, whenever the optical topology changes from elliptical to hyperbolic regime, you have reduction of lifetime. So all of this is nice and well until our experimental collaborators decided to make material better. And the way they make material better, they start with their nanowire arrays, and then they anneal them at, I forgot, about 800 Celsius, I think. And what that does, it essentially makes nanowires more smooth because the gold in nanowires is solution grown. And so when you anneal that gold, presumably the different components of gold that are deposited from solution become basically mold closer to each other. And so what they saw is that instead of this peak growing up as it should from the effective medium standpoint, this peak splits. And so that was a big puzzle of why would it split all of a sudden. And so that's where this story of spatial dispersion comes in. We started looking for a second wave that propagates in these materials using theoretical analysis. And so what we've done, we've modeled the light propagation in a composite from sort of composite standpoint, assuming not just that you average the fields, but actually looking at the modes that the true nanowire composite would support. And so these are the dispersions of the modes that one would expect to see. And these are the dispersions of the modes that come from the finite element solutions of Maxwell equations. And what you can see is that the elliptical modes or the circular modes that are not affected by anisotropy, they are perfectly modeled by effective medium response. The high wavelength dynamics, again, is hyperbolic and perfectly modeled by effective medium response. But this low wavelength regime is interesting, and there we numerically can identify two different modes. And so if we want to put the second mode into effective medium response, then what we can do, we can say that that our effective medium parameters now depend on the wave number. So the extra mode originates from the surface plasmon polaritons that propagate on nanowires. And you can see that on average, if I average this field over a unit cell, I do get longitudinal field dynamics because the mode would propagate up the nanowire, and the electric fields that you can see here, they are pointing in the same direction. So long story short, this is just an introduction part of the talk. We can put this effective medium into or put the spatial dispersion into our effective medium. We can perfectly describe, as you can see on this slide, this double peak appearing in the extinction spectrum. We can relate these new maxima to the interference of the two waves that propagate inside the materials. And then so for me as a theorist, it's very interesting to see how experimentalists can actually validate your theoretical approach. People can study the near field distribution of electromagnetic fields in these nanowire composites and actually recover these crescent type shapes that represent the signatures of our longitudinal waves that propagate in these materials. So it's all nice and well. And if you talk to metamaterial community researchers, this is what you would hear when they talk about non-locality. This is what we call now effective non-locality, because it is driven not by the non-local response of underlying components, but by material nanostructure or microstructure. So this non-local response is essentially a reminiscence of this photonic crystal regime where the material sort of homogenizes to effective medium. What happens to these modes as you make the granularity smaller and smaller is that these longitudinal waves become extremely high index and become limited to essentially epsilon near zero regime of your material. And then you don't see them anywhere but near the zero point of your permittivity. And then the material effective medium essentially converges to what the local effective medium should do. But there is more to it, and more to it in a sense that people have started looking at the arrays of nanoplasmonic particles positioned very close together. So these, there are some experiments and there are some simulations, and these come from the computational chemistry community primarily, where instead of modeling permittivity as whatever Pelic or other textbook gives you, they actually model the electron response from the first principles. And so this is a toy model from the plasmonics community where they put two metal particles closer and closer together and analyze the dynamics of this hotspot that emerges in between the particles. So classical local electromagnetism tells you that the hotspots should become stronger and stronger the closer the particles are. But these full wave and full hydrodynamic simulations essentially show you that the hotspot goes up and then it disappears as the particles come closer to about closer than about 1 nanometer. Researchers identified that this behavior, so this disappearance of the hotspot, is caused by non-locality of the particle itself. So this is non-local response of the material as opposed to of the microstructure. And so here it looks like this inherent non-locality yields some small quantitative correction to material response at extremely small length scales. So on the other hand, as I showed you at the very beginning, Pekar showed that non-locality should exist. And people in the 60s and 70s did look for the signatures of non-local response. The nanotechnology at the time was not as developed as it is now, and people looked at non-locality in phononic materials. And so you can see that these are the experimental reflection spectra from cadmium selenites at 4 kelvins. And so at 4 kelvins, they see this peak in reflection response that is not modeled by classical simulation. And this peak is attributed to actually excitation of that additional wave inside these cadmium selenide crystals. So I want to point out that these are literally 1 to 4 Kelvin temperatures. And people who do these experiments, they say that the experiments are so sensitive that they had to do these at night because a running trolley bus would destroy their crystal and make it not pure enough to be able to support these additional waves. So now this is sort of the story up until now. We have the quantifiable quantitative corrections to non-local response of isolated nanoparticles, and we have a qualitative corrections to response of macroscopic crystals. So the goal of my talk, the remaining part of the talk, is to put the two and two together and analyze what would happen if you build now a composite from non-local components. And so before I start talking about what the results we got, I want to point out that the moment you have additional waves, and this has been realized for a while already, you have an additional problem. And that problem is that now it's the conventional boundary conditions that come from EMAG and that we teach in EMAG, they are not enough to calculate the amplitudes of these additional modes. And so you need the additional boundary conditions. And you can see, luminaries in the field have been argued about the origin and the form of these additional boundary conditions for now decades. And so to solve this problem, what we propose to look at a composite not as a set of discrete layers, but as a material that has some relatively smoothly for the beginning change in permittivity and non-locality. So this is our displacement field in the limit of relatively weak non-local response. Non-locality is here. You can see that this is essentially dependence of displacement field on the derivatives of electric field. This has to be a second derivative for the inversion symmetric materials. And then the form of this equation is basically dictated by the fact that D dot E should be an energy of the system, and energy should be a self-adjoint operator if you start with materials. What I'm going to be showing you, I'll be talking about a composite that is multi-layered structure. It's easier to describe, and I think it catches most of the new physics that we discovered. So this formalism can, in principle, be extended to cylinders, spheres, and other composites, but these are not results that I'm going to show you. So once you have this displacement field, you can, in the layered geometry, convert Maxwell equations to essentially one differential equation for one component of the field. It happens to be the component of magnetic field that is perpendicular to the propagation of light. These are so-called transverse magnetic waves. Equation is complicated. You really don't need to analyze it in greater details. What I want to point out is that now if we take this equation and look at the transition of this equation to step-side composite, we can actually recover the boundary conditions that should be satisfied for the solutions to make sense, for the solutions to be finite. And so these boundary conditions require continuity of B, tangential E, normal E, and this combination of the E derivative and non-locality. So I want to kind of slow down here for a second. The first two conditions are completely consistent with local electromagnetism. So these are your primary boundary conditions that we teach to our students in EMAC classes. The second two are the additional boundary conditions that we were looking for. Out of the second two, the last one is more crucial to calculate light propagation from local to non-local material. The EZ seems to be played out by itself in that case. And then when you have a boundary between two non-local media, all four become necessary, and you have to enforce all four. I also want to point out that B cross E, so this relationship gives you continuity of the local part of the points in flux through the interface, and then the product of these two fields gives you continuity of non-local part of the points in flux through the interface. So all of these four wave continuity conditions, they essentially follow energy conservation requirements that come from Maxwell equations. So once we have boundary conditions, we can look at the multi-layered composites that I promised you to look at. We can embed these into non-local analogs of the transfer matrix that we can easily develop, or let's put it straightforwardly develop. We can look at the light propagation in multi-layered composites. We can look at the dispersion of the waves in non-local periodic arrays of layers, which are essentially 1D photonic crystals. And so all of this can be now done once we have the boundary conditions. So I just want, before I show you the results, I want to show that this formalism that we propose does not break anything that we already know and sort of have at the back of our mind when we talk about electromagnetism of weakly local materials. So that's, again, our D field. So what the main outcome of this talk is that this alpha essentially introduces a new, what we call primordial length scale, or the inherent scale of non-locality of every material. It is related, as you can see, to operating wavelength and square root of alpha with some factor. If you start plugging in numbers for dielectrics, this primordial scale is of the order of nanometer. This is exactly the scale where the plasmon resonance between the two metal particles disappears. For plasmonic materials themselves, this length scale is given by the ratio of Fermi velocity to speed of light. times the wavelength. And depending on the metal and plasmonic material, it can be from 1 to 100 nanometers. Most of the plasmonic materials we're operating with would have it at 100 nanometers type. And then phononic materials that sort of operate on phonons that are very large, spatially large excitations. They have primordial length scale of the order of microns, and that's why people saw the excitation of additional waves in the single layer phononic material. So let's take an example of a plasmonic material. So that's our dispersion of permittivity now. So you have the K dependence here as a correction. As I promised, Fermi velocity is right there. We can calculate now dispersion of the two waves that propagate in this material. These are the blue lines on this plot. What this plot and other plots in this talk show, they show the square of effective index. So when the square is positive, you have propagating light. And when the square is negative, you see evanescent modes or reflection. So as we know, metals reflect for larger wavelengths. So that's this regime right here. And then for shorter wavelength, metals are transparent. And so that's this regime here. And you can see that now instead of one wave, that is like a blue line and the red circles that you see at the bottom, we have a second wave. And so this second mode, that's the result of adding non-locality to our response. You can see that the second mode has humongous index, couple of orders of magnitude larger than the index of your main mode. And as a result, you really don't expect light to couple to it because of the huge impedance mismatch. And so, in fact, if we calculate reflection with non-local theory, that's the line, or with local theory, these are the dots, we get identical results. So once again, small non-locality, if you start including it in the macro scale system, doesn't add much to the dynamics that you see. So let's now look at the metamaterials, and we start with bilayered composites. We start with layer size that is comparable to wavelength. And as I showed you at the very, very beginning, this is expected to be photonic crystal regime. So what you expect to see several bands and several band gaps. And again, positive K squared, those are the bands, and a negative K squared, those are the blue lines, those are your band gaps. So this is the photonic crystal dispersion that you expect to see in this material. This is what would happen if you add non-locality. You have that same dispersion of the main wave, and then you add additional wave that again has humongous negative index squared. So therefore it evanescently decays inside your composite, and really it doesn't really matter. Now, you make material smaller. I showed you that you should converge to metamaterial. That's your metamaterial. This metal dielectric composite should exhibit that, again, this hyperbolic transition. So that's the frequency of elliptic to hyperbolic transition that you see here. This is just local calculations. And at the bottom, we see what would happen if you add non-locality. And you can see nothing happens other than, again, a second mode that is evanescently decays inside the composite. So now, from this point on, if I start reducing the layers thinner, thinner, and thinner, the predictions of local calculations won't change. In fact, these are the predictions of local effective medium theory. So this is a brick of material with these parameters. And so I will not show you these anymore. But now, as I change the layer size, what we see is that the dispersion of the modes changes dramatically. So first, the single resonance that corresponds to elliptic to hyperbolic change shifts and splits in two, and in fact in many. Then these modes start evolving, and this additional wave that used to be evanescent pops up and becomes propagating. And then eventually, when your layers are extremely thin, you converge, the behavior converges to some effective medium response, that, as you can see, completely different from what you expected to see. Now, it came to us as a surprise. You can develop effective medium theory for non-local case, and in fact, we did. The real surprise is that the parameters for this non-local effective medium are not local with a correction. They are completely different in this case, ZZ response, and which response is different is basically driven by geometry of metamaterial. In our case, it's multi-layer stack. So layers are, vertical, and therefore that's the response that becomes different. But basically what this tells you is that one effective medium cannot transition to the second effective medium by itself. You have to go through this weird process of what we call primordial metamaterials, where essentially the dynamics is now interference-based, driven by the primordial waves. So these calculations, obviously, they don't just change dispersion, they change transmission. And again, instead of transmission being constant, you see a transmission evolving as you make layers thinner, thinner, and thinner. And again, convergent to effective medium non-local response. So this is sort of a map as we see it now. So this is the map of material response that has two new regimes. We have a regime of primordial metamaterial where the scale of material now is comparable to the inherent scale of non-locality of the component. And in contrast to effective medium, this regime is sort of similar to photonic crystal, but has much thinner layers generally. Your dynamics is dominated by the interference of the waves propagating in this now non-local crystal, and cannot be described by effective medium parameters. And then finally, there is effective medium response where the fields become smooth again, but now your material is non-local. So the summary of the theory part of this work, we essentially looked at this picture that we have been, and again, I've been teaching this picture for several decades. And we looked at what would happen if you take into account material non-locality into consideration, and we basically discovered two new material regimes. The exact boundaries here are obviously driven by the component shape, component size, and non-locality of your component. And so it comes to the point that the theory is good, but one has to validate this in experiments. So if we want measurable non-locality, we have to have composite with good interface quality, room temperature operation, and measurable non-locality of the components. And so we already know, I already showed you that plasmonic layers have non-local response. And so this is the material stack that our UT collaborators grow. The one component of the stack is this highly, highly doped indium arsenide semiconductor layer. So this is a plasmonic layer that has non-local response because of the Fermi velocity of electrons. And then what we've done, as a non-local dielectric, we have a 3-layer stack where there are two barriers that sort of prevent electrons from moving. And then there is a low-doped indium arsenide layer, doped low enough so that it still is dielectric and its permittivity matches these barriers. So from the standpoint of local EMAG, this is a homogeneous layer. And from the standpoint of non-local EMAG, this is a 3-layer system where the thickness of the barrier controls the non-locality of the overall system. And so what we see, I will use maybe 2 more minutes of your time. When the barriers are thick, we see in transmission a single dip. And these are our calculations. And you can see that this dip is reproduced in calculations. And we see that it is because of that elliptic to hyperbolic transition in these multi-layer composites. And when the layer size is thin, the dip splits in two, just like in our calculations of the dispersion that I showed you. And we model this dip as a non-local response, a primordial non-local response of this multi-layer structure. But now there is more to this. So we basically reproduced one data point, but there is more to this because, as I showed you, primordial response is not effective medium. So as we change the period of the structure, we should be able to control the dispersion of these modes, and we should be able to see that in the optical response. And indeed we do. So as you can see, as we change the thickness of individual layers, keeping the composition constant, we can drastically change the optical behavior from this to this. And what I want to point out is that the non-locality mode essentially moves from almost 7 microns to almost 5 microns. And so this is unique to, this behavior is unique to our primordial response, because now the signatures of non-locality are not anymore tied to epsilon near zero regime. Basically, they can be controlled by the overall structure of the system. And this behavior is sort of like behavior that we saw in photonic crystals, where we were able to design optical filters by just changing the thickness of then local materials. So that's the summary of the talk. We developed a description of composites that have non-local components. We propose the existence of the two new electromagnetic regimes that are dominated by this primordial inherent non-locality. And we realized one of these regimes, this primordial metamaterials, in experiments. Thank you.
Okay, we thank Professor Ryukhtin for this interesting talk. Now this session is open for questions. Is there any questions?
I'll stop sharing so I can at least see the field of faces.
Yeah. If anyone has a question, please just raise your hand. Okay. So. If no question, okay. Now let's thank the Professor Ryukhtin for his interesting talk again. Okay, thank you.
These participants sent a video record, so we share this record because they cannot to present it by itself. Okay.
Yeah. Okay. So the last talk is just a video presentation. Yeah. Okay, we have the last talk for this afternoon session. Okay, because the co-authors cannot just participate in this conference, so they have already sent us the video. Okay.
Okay.
Yeah. The staff, is any we cannot hear any sound.
I try again.
Well, good morning, ladies and gentlemen. I'm very happy to be here. that. Thank you for, I said good morning, maybe some time presented. I would like to thank you very much for your invitation. I'm very pleased to be here, but unfortunately, I have to present in China as well, so it's not possible. Yeah, not a problem. So now I'm going to discuss with you some relationship between light electromagnetic scattering and acoustical scattering. And I'm very pleased to present my collaborators, Radu Malureanu from Brazil, Shanghai, Sao Paulo University, and Shen from USST in Shanghai. To begin with, I have to tell you a bit the story of electromagnetic scattering. Actually, the first paper I have done on this topic is dated 82, and it's called a generational mystery, more than 4 decades ago, you know. It was a long time ago. And in this paper, the name is in French, Génération de Lorentz, which is very easy to translate, and it's just a generalization of Lorentz mystery. And discuss the interaction between the laser beam in the on-axis configuration and the spherical particle. So it was the beginning of now is known as the general. Next one, the theory has been developed for many years, like about 10 years to develop the theory, and about 30, 14 years before having the first application of it. And here are the topics which have been developed. First of all, you have to discuss the description of laser beams. In general theory, the entails. Laser beam is encoded by a set of coefficients which are called beam-shape coefficients. Beam-shape coefficients are very important because they appear in any quantity in the theory. In the description of the incident beam, making all quantities, cathode beams, and so on. Second problem which has been studied is the mechanical effect of light, force, torques. You know, for instance, that in 2018, Ryukhtin got a Nobel Prize in physics for the optical lasers, and the GMT is able now to compute the force and torque exerted on particles with a very lot of accuracy. So after we have to study electromagnetic scattering for various beam shapes and various scatter shapes and morphologies, it's spherical coordinates, cylindrical coordinates, elliptical coordinates. And you can also study the internal field and the resonances, and more important, the optical particle characterization. Optical particle characterization has been and is the original motivation for the development of general optics. Now, this 4 decades later, I recently published a review paper on the period 2019-2023, which is multi-matrix method for electromagnetic structural beams. And this review just focused on papers which quote my own paper. That is to say, you know, I'm sure to have something which is very comprehensive for the interaction between laser beam and scatters. And in this review paper, you have more than 700 references for outside experiments. So you see, there's a lot of contribution in this field for all the topics which can be developed inside animation. So it's a huge field of research. And now that's the prime. All this field of research that has been developed for 40 years can be transferred to acoustical scattering. This is something which is very unexpected for me 3 years ago. And why it is possible? How is that possible? Well, first, just recall a few things. Generational speciology, GLMT, and there is another technique which is called EPCM, Extended Boundary Condition Method. Both are P-matrix methods. P-matrix is something which relates the scattered field and the incident field. And when you can compute the relationship between both of them, you can construct a P-matrix, transition matrix. And both of these techniques, GLMT and EPCM, are P-matrices. GNT is for spherical homogeneous particles at the beginning, and then has been developed, as I said before, different kinds of scatter in different morphology. And EBCM is for arbitrary shaped particles. In both cases, the intent fees may be written with the same equation for the incident field, just electron field. You have a summation, double summation. You have some functions which are known as being vector spherical wave function, very well known, and some coefficient AM and BN. Actually, you can manage a bit to replace this coefficient by other coefficients, which are what we call the beam shape coefficient, GN, PN. TN is transverse magnetics, it corresponds to one special solution of the Maxwell equation. And T is transverse electric, which corresponds to another solution of the Maxwell equation. The general solution of the Maxwell equation is obtained as being the summation of the TN and the P. Now, to translate electromagnetic scattering to acoustical scattering, you must have some analogy. Here's the example of analogy. In green over there, you have the electric field, the magnetic field, radial component, and they are expressed by this expression. In green, just forget, it's not important. In red, you have vector spherical wave functions that I discussed just before, they are explicit. You have Bessel function, associated correlation function, and some analytical exponents. And the GNLPM and the GNLPM. You have two equations because the electromagnetic vectorial field, you have the equation for the electromagnetic component, the electric field, and one equation for the magnetic field. And now look to the acoustical field. The equation describes the acoustical field is exactly or nearly exactly the same. Again, some simple rings that you can forget, and the same function. And that's how you can introduce some GNL, L means acoustical, which are the beam shape coefficient for the acoustical field. So when you compare that, you say, my God, it's so similar, it must have some relationship or something. There is at least two other analogies can be discussed, Shen. So this started in 2023, and at the present time, elements have been published or seen in different telecoms. So lots of applications have been. And the most important relationships we can obtain are the relationship between the electromagnetic and the beam shape. Here's an example. On the left, you have the electromagnetic beam shape coefficient for the transverse electric case. And you see they are expressed in terms of very, very beautiful expression in terms of the acoustical beam shape. Very simple. To get this expression, you need about 200 pages of computation in format, so this heavy calculation, but the result is just very good. This is important actually because you see, you have only one example of one case for the acoustical beam shape coefficient, and you have two kinds of electromagnetic beam shape coefficient. So these two kinds of electromagnetic beam shape coefficient can be expressed versus one simple case of acoustical beam shape coefficient. Basically, it means that you can have your calculation increasing the speed by a factor of 2. This can be very important. This kind of factor of 2 can be very important, in particular when you want to compute beam shape coefficient with numerical quadrature, which are very expensive in terms of time computation. So this is just an example of them. Maybe I shall have to speak up. Now, look at the approximation. Once the GNFT has been built at the beginning, we needed 1 hour to compute one beam shape coefficient. It was impossible to use this theory for whatever you want. It took more than 10 years to solve this problem. And one of these problems has been to invent what we call the localized approximation, which is a very fast way of computing the beam shape coefficient. On the left, you have the electromagnetic case where you see you just decompose the electric field, radial component, in terms of azimuthal mode, and each azimuthal mode has this expression. You remove this, just keep that part, and in that part, replace the radial component by a certain quantity, which is L, 1/2, and the angle theta is just given the value per unit. And the L is found to be N plus 1/2. This is very, very simple to implement, and it can accelerate your computation by the third order of magnitude. It's very fast now, and it's has been the way to use it. Now, acoustical case, you can also develop localized approximation. It's just very similar. There is a small difference. The value of N is slightly different. Then, in both cases, electromagnetic case or acoustical case, we can have very fast computation now, which are possible. This is an example of comparison between quadrantures and localized approximation. Quadranture is the original way, exact original way of computing the Bayesian coefficient, and localized approximation is about, I said, 2 or 3 orders of magnitude faster. And you see the argument is very bad. That's just an overview of what I wanted to say. And the story goes on, obviously. And in particular, I hope to see you at the next event in 2026 in Wang, where we organize the LIT conference, the Light Interaction is particular, together with the LI workshop, which is laser induced condensates. And I really hope to see you more. July 5 to 10. Thank you very much for your attention.
That's all. Thanks for the speaker.
Thank you very much. Unfortunately, this present is absent due to the technical reasons. He sent us this video, but it's not a very nice sound. But we have this presentation. Thank you very much. Thank you, the chairman of this session. And now at 4 p.m. Kyiv time, we start our poster presentation, poster session. You can connect by the personal links of each presentation. And tomorrow we will meet at 10 o'clock. It will be our last conference day with biomedical presentation, biomedical directions of investigations, and will be the closing ceremony. Thus, thank you very much, and see you tomorrow. Thank you. Goodbye.
Thank you. Yeah. Bye.
Bye.